Greetings. Welcome to the second part of presentation 6.1. Okay, this is week 6B is the name of this presentation. And we're just going to continue where we left off. And I believe we left off at this point right here. Before that, we did, well, there's no point in me recovering, summarizing all this business because you've just finished watching the other video. So now we're on to binomial coefficients and identities. The binomial theorem is very well known, very well presented throughout all kinds of textbooks, including discrete math books. And it's basically there because it is such a nice educational tool. I've never in my life used it in any kind of a research paper or any kind of derivation outside of just displaying its beautiful features. Just hold on a sec here. Its beautiful mathematical structure in a pedagogic sense, okay, for teaching. Okay, so section summary, we're going to show you a new proof technique. It's called a combinatorial proof. I said this is combinatorics. So there's a way of proving things by counting. We learned that we can count things by direct proof, by indirect proofs, including a contradiction, which is the most common proof tactic. Combinatorial proofs, on the other hand, usually involve problems where you can count. And there's two ways of counting it from one side to the other, and also there's a bijective way of doing it. We'll define what bijective means shortly. Okay, binomial theorem, like I said, Pascal's identity, which is directly related to the binomial theorem, and other identities. So we introduce an alternative notation now. I think we've said this before. It seems to me that I've said this on the last presentation. So n choose r combinations now is noted with this notation here. N choose r. So that's meaning the same thing, but this is known as a binomial coefficient. And a coefficient, of course, is a constant term in front of a variable, say in a polynomial. Ax squared plus bx plus c. A, b, and c are coefficients. All right. So combinatorial proofs, let's just look at that. Give a combinatorial proof of the identity 2 plus 2 plus 2 equals 3 times 2. Okay, so this is amenable to counting, and I'm just showing this to you as an introduction to the technique. Question, how many two-letter words start with A, B, or C and end with either Y or Z? Okay, answer, there are two words that start with A, two that start with B, two that start with C for a total of 2 plus 2 plus 2, yes. Answer 2, there are three choices for the letter first letter, two choices for the second letter for a total of 3 times 2. So that is showing how you can count this side to be equal to counting this side with a different technique. So there are two words that start with A, two that start with B, two that start with C, and there are three choices for letters for first letter and two choices for the second letter. So there you go. Three choices for the first and two choices for the second. How many two-letter words start with A, B, or C and end with Y or Z? So that fulfills those characteristics. That is a combinatorial proof. So combinatorial proof of an identity is a proof that uses one of the following methods. One, a double counting proof uses counting arguments to prove that both sides of an identity count the same objects, but in different ways. That's kind of like what we did here, right? We counted two different ways, one by pure addition, one by pure multiplication. And bijective proof shows that there is a bijection between the sets of objects counted by the two sides of the identity, i.e. selecting K children to be rewarded with ice cream cones out of a group of N children, which is the same as choosing instead the N minus K children to be denied ice cream cones. So you look at one half of the one sample of the population, and then you look at the complementary half of the population. So you go bijectively. That's what the bi part means. It means two-way approach. Bijections are something, just keep in mind. You'll become more comfortable with that term when we study in chapter 9 functions, bijective functions, for example. Here, a bijective proof simply means that, say, you're selecting k children to be rewarded with ice cream out of a group of n, or it's the same as choosing n minus k children that are denied the ice cream. You can see how that works. That's a bijection. Bi means two paths. So a bijective proof is a proof technique for proving that two sets have equally many members, or that the sets in two combinatorial classes have equal size by finding a bijective function. There we go again. This is ahead of its time. Just accept it for now. We don't know what a bijective function is yet. We'll find out in chapter 9. So in a way, this is out of place, but some of you might already know a bit of function theory enough to know what a surjective, injective, and bijective function is. There's three kinds. That maps one set one-to-one onto another, okay? So a bijection is a one-to-one correspondence, okay? Bijective proof is a technique for proving that two sets have equally many elements, or that the sets in two combinatorial classes have equal size by finding a bijective function that maps one set one-to-one onto the other. Okay, so just accept that for now. You don't need to really understand this until we hit chapter 9. So that's just a taste of what's going on, and that justifies what we mean here. This is good enough for you to understand what a bijective proof is by looking at this example with children and ice cream. Okay, let's have a look at this now. What we want to prove now is that there's symmetry in Pascal's triangle, as it were, which we'll see shortly. Here are two combinatorial proofs. So n choose r is the same as n choose n minus r. So that's kind of a bijection in itself, you see? Here we're choosing r, and here we're choosing the other complement, n minus r, of n objects, okay? So when r and n are non-negative integers with r less than n, obviously r can't be greater than n for a non-repetitive combination. So let us now just prove this, okay? All right, here we go. So bijective proof. I think that's working, yes, bijective proof. Okay, suppose that set S is a set with n elements. There we go. The function that maps a subset okay, here I'm using this notation to say width. I'm using this shorthand to say function. Okay, I use this shorthand for theorem. Okay, so the function that maps a subset A of S to its complement, that means the complement of the set, is a bijection between the subsets. Of S with R elements. Is that coming through okay? Yeah. And the subsets with n minus r elements. Okay. Since there is a bijection, between the two sets, They must have the same number of elements. Okay, that proves it. QED. Okay, so that's the bijective way of proving the symmetry of these binomial coefficients, that n choose r, okay, is the same as n choose n minus r. Okay, so that's what we're proving, that these binomial coefficients are symmetrical about r, n minus r, I should say. Double counting. So this example allows us to explore both of these methodologies. Okay. By definition, that means definition. By definition, the number of subsets of S with R elements is n choose R, obviously. N choose R. All right. Each, what am I doing for space? Okay, each subset A of S can also be described by specifying which elements are not in A. Okay, which elements are not in A, i.e. those in A complement. Okay, since the complement of a subset of S with R elements has n minus R elements. You see how this is going. There are also n choose n minus R subsets. God almighty. Of S with R elements. QED. Okay, so these are two methods, bijective, double counting, of proving a very, very basic combinatorial identity. N choose R equals N choose N minus R. This identity is easily proved by both techniques. This is more pedagogic than anything. Okay, I hope you appreciate that. So let's just go back here. I mean, you can see it's all here, what we've just done. Let's now talk about the binomial theorem. Okay, let's just get to the meat of it. Okay, so those of you that haven't seen the binomial theorem before, just here we go. Those that have, please bear with it. Okay, I have no idea what that is. Okay, so just note that Okay, a binomial, of course, is as opposed to a monomial, which is like x to the n. A binomial is x plus y to the n. It's a binomial. There's two terms that are raised to a power. And so if we expand it out here, x plus y to the 0th power is just 1. If it's raised to the first power, it's just simply x plus y. But however, things start getting complicated the higher powers we go, and you can see how it expands out. And we note a few kind of strange things. One, the the x's, the powers of x's decreases, okay, as you go in. Cubed, squared, linear, 0, or constant. And it keeps going on like this. And so, as you can see, they're symmetric about the middle. There's some symmetry about the middle. So these coefficients, 1, 4, 6, 4, 1, for example, 1, 5, 10, 10, 5, 1, you can see they're symmetric. That brings us back to this, is which we tried to prove, the symmetry of these coefficients. Okay, these coefficients in front are binomial coefficients, as we'll soon see. So how do we represent this in a compact form? Well, so x plus y to the 4th is this, descending powers of x, ascending powers of y, symmetric pattern of coefficients, like we just said. So we call these things binomial coefficients, 1, 4, 6, 4, and 1. And they fit into this well-known pattern, a geometric structure called Pascal's triangle. So here's 0, choose 0, 1, choose 0, 1, choose 1, 2, choose 0, 2, choose 1, 2, choose 2. So this is the third n, the n equals 4, n equals 5, and then you can see the r's go down this way. So here we have the r's 1, 3, 6, 10, 15, 21, all right, as we go down successfully to higher powers. And we note that the sum of these two produces this one in front, Pascal's identity. 6 choose 4 plus 6 choose 5 equals 7 choose 5. And so that's basically what we have right here. 6 choose 4 plus 6 choose 5 equals 7 choose 5. And that's these numbers right here. That's what these binomial coefficients actually end up being. Okay, so that's Pascal's identity. We should be able to prove that. First of all, n choose 0 equals 1 and n choose n is 1. So we know that the outside of this triangle is just 1s. You can see how that works. Okay. N choose k is the same as n minus 1. Choose k minus 1 plus n minus 1. Choose k. That is Pascal's identity. Here, this is the symmetric identity that we just proved. And also, we can see that the sum of the coefficients alone is 2 to the n. Now, how can we get this related to Pascal's identity? Sorry, to the binomial formula. Well, it turns out, if you look at this, that if we could just get these powers, the x's and y's, to just be 1, then we're adding up just the coefficients. So that means x equals 1, y equals 1. And in that case, the x's and y's are just 1 throughout, and you're just summing the coefficients. That's where this comes from. And it's 2 to the n because we've got 1 plus 1 is 2 to the n equals the sum of these coefficients. So you can see what we're talking about there. Our goal is to establish these identities. And here you can see, again, we've seen this before. This is just simply n choose k, has this analytic form, n factorial over n minus k factorial times k factorial. So that's what these binomial coefficients are, related back to n choose k in the introduction of combinatorics. Okay, Pascal's identity. Let's have a look at an algebraic proof. This is pretty simple. Pascal's entity can be both proved algebraically and combinatorically. I'm not sure what exercise 19 means. Maybe this is Rosen. I forgot to check. Okay, so what do we have here? Okay, by definition of n choose k, we have n minus 1 choose k minus 1 by the definition of n. By this definition here, it equals this. So that's n minus 1 factorial, as you can see right here. N minus 1 factorial. N becomes n minus 1. K becomes k minus 1. So you just put that in the denominator, you simplify terms, and you end up with n minus 1, choose k, equaling these terms right here. So, that's just summarizing the top of what we've done here. So now when we add n minus 1, choose k to n minus 1, choose k minus 1, and again, using the definition of the binomial coefficients, you do some algebra and you end up with the same, you end up with the same guy. Okay, here we go. Algebra all the way through here, and we end up with these two, with a little bit of algebra equaling n choose k. So that's here. This is a little bit different form from this. We've shifted. So instead of n plus 1, we have n minus 1. Instead of n, we have, well, n's there. You have k and k minus 1 over here. And it's just a shift of the coefficients. I should have actually made that explicit up here. You can check that for yourself. So they say the same thing. There's just a shift in the indices. That's all. But they still say the same thing on Pascal's triangle. Okay, that's the whole point. This is the one further down. This is this one down here. Okay, the one that has the larger n value. Okay, that's the larger n value here. And this is the previous terms above it. Okay, the previous terms above it, which is 1 less n from 7 to 6 in this case. You see what I'm saying? And you end up proving the identity. And we've done it here again with a slightly different shift in the indices. You can figure that out on your own. Maybe I should have put this in the same proper form, but I didn't. I'll fix that later. I'll fix it and send it out so that it's done properly. That's just a little sloppy here. But anyway, that's a simple algebraic proof. Now, how about if we look at this combinatorial proof? Uh-huh. All right. What do we have here? A combinatorial proof. My God. Okay. Let's see. We want to prove that n plus 1 choose k equals n choose k minus 1 plus n choose k. So the combinatorial proof is as follows. So let T be a set where the absolute value of T equals n plus 1, and A is an element of T, and S equals T minus the set containing A only. Okay, all right. So let T be a set where the modulus of T, the cardinality of T, is n plus 1, and let A be an element of T, and let therefore S, the set S, be T minus this small element in T. Okay, so the reason why we're doing this is we're picking out out of a set, we're looking at a particular element to reflect the structure of this proof right here. So we have n minus k, n plus k, n here. So that's the setup here. We're going in the direction of showing the difference between the two rows of Pascal's triangle. Okay. Okay, there are n plus 1, choose k, subsets of T, obviously, containing k elements, obviously, by definition. Each Okay. Each of these subsets either contains A with K minus A, okay, A with K minus 1 other elements, or contains K elements of S and not A. Okay, that's clear. That's obvious. Each of these subsets either contains A with K minus 1 other elements, or it contains K elements of S without A. I mean, that's obvious by construction. All right. So here, let's just keep going. There are okay, and choose K minus 1 subsets of K elements subsets of K elements that contain wait a minute. There are, and choose K subsets of K elements that contain, that's right, A. Since there are, and choose K minus 1 subsets of K minus 1. K minus 1 elements of S. All right. Let's keep it going. There are also, and choose K, subsets. That says subsets, believe it or not. subsets of K elements of T that do not contain A, because there are and choose K. See, you can see how we're just basically describing the result of this way of describing the elements with this particular element A with each of these terms individually. Okay, so because there are, and choose K subsets of K elements of S. Oh boy, oops, went off my sheet. S, okay. Hence QED. So that's a counting argument. Let's just go back to it. So there it is. Basically, let's just go through it again. Okay, you've got to study this. You've got to be able to do this combinatorial proof on one of the exams that's coming up in this course. You have to understand combinatorial proofs. This is probably the best one that and the proof of the binomial theorem. Okay. Okay, this is Pascal's identity, and we're proving it combinatorially. We proved it algebraically. You should be able to do that on a test in this course, midterm 2 or the final exam. You will have a question like this, that's for sure. Prove this algebraically and combinatorially. This particular problem here, yes, you can. You can research this. If you don't understand the argument that we made, it takes a while for this argument to sink in, but it's very simple after you appreciate it, after you see what's being done. This summarizes it here. When we take this particular arbitrary constant A or element A in the discussion of set T of size n plus 1, where A is an element of T and S is T minus this element A. Okay, so it's a set T that's slightly smaller. It's missing this element, and that's how you come up with this using that structure that's in the Pascal's identity to make this combinatorial argument. Okay. Pascal's identity, okay, simply stated, consider n balls in a basket. Let there be one red ball and n minus one blue balls. Now look at the number of ways of choosing r balls in two different ways. One way to choose r balls out of n balls, so one way is to choose r balls out of n balls, so the number is n choose r. The other way is to look at the cases where out of the r balls chosen, if we have a red ball or not. Same argument. That's our constant A. We have only two options, namely out of the R balls, we could have one red or no red. Okay, it's the same argument that was made here. So study this and you will understand this combinatorial proof. I mean, we've basically all I'm doing is restating what's been said here in a simpler way with balls instead of actual variables. So here's another combinatorial proof. N choose 0 is 1 and n choose n is 1. I mean, that's pretty easy. Let's just look at it. What do these coefficients tell us? N choose 0 gives the number of ways to select 0 objects from a collection of n objects. Well, there's only one. There's only one way to do this, namely to not select any objects. Thus, n choose 0 equals 1. Similarly, n choose n gives the number of ways to select n objects from a collection of n objects. Obviously, there's only one way, okay? So you could look at the alternative ways of explaining these with bit strings and yet another way. So study this by yourself. I think this is educational more than it's illustrative more than anything, but we threw it in anyway because it's nice and wordy. You can read it on your own. So we just proved this. What's going on? Didn't we just prove this? Oh, man. Yeah, we did, didn't we? We proved it right there. Well, okay. Yes, we proved it exactly the same way. What's wrong with me? I'm losing my mind. Yep, bijective proof and double counting proof. That's how we introduced it. I see now that I used this in the beginning to introduce these two, and I forgot that I did that in this later version. So this is the same argument that we gave earlier, and you can tell me whether it's bijective or double counting. Okay. So the binomial theorem itself is this progression of binomial coefficients with the descending powers of x and ascending powers of y is easily described by the summation right here. Sum from j equals 0 to n for the expansion of x plus y to the nth power is n choose j times x to the n minus j times y to the j, which if you expand the summation out is exactly these terms that we talked about right here. It's these terms here that we talked about. So you can see that's what we're doing here. We're providing a simple, compact way of describing this progression up to any arbitrary number n. Okay, that's good to know. All right. So a combinatorial proof is trivial. The terms in the expansion of x plus y to the n are of the form x to the n minus j, y to the j for j equals 0 to n. To form the term x to the n minus j y to the j, it is necessary to choose n minus j x's from the n sums. Therefore, the coefficients of x to the n minus j y to the j is n. Choose n minus j, which equals n choose j. Okay, remember, these are symmetric. These coefficients are symmetric. We proved that here. Okay, so that proves the binomial. This right here could be n choose j minus n minus j. They're the same. Okay, so that's the binomial theorem. You must know this. You have to memorize it. Make sure you know how to manipulate it. So, for example, what is the coefficient of x to the 12, y to the 13 in the expansion of 2x minus 3y to the 25? Well, we view the expression as 2x plus minus 3y, right? To the 25th power by the binomial theorem. You plug in all these values into the formula, just tit for tat, it's up to 25, and then you have j running up to 25 as well, and you have this x with a 2 in front, and you've got the y's with minus 3, as well as the coefficient in front of it, and so consequently the coefficient of x12 y to 13th in the expansion is when j equals 13, and you can see what it looks like. These are common problems to use. I just find that these are useless kinds of problems. Who would ever want to know what the coefficients are, an arbitrary place in an expansion of the binomial theorem? So I'm not going to ask this kind of question. I kind of find that it's interesting. You can see how you can use the binomial theorem for a purpose that's just not that interesting. This one, on the other hand, we already saw this, that the sum of the binomial coefficients at 2 to the n, well, we already proved that that's simply by having x equals 1 and y equals 1. That's where the 2 comes from. 2 to the n, you see? And therefore, all the x's and y's turn into 1s. And so you're just simply summing the binomial coefficients. So you have a look at this combinatorial proof. It's practically self-evident. Okay, exercises. An alphabet of 40 symbols is used for transmitting messages in a communication system. How many distinct messages, lists of symbols, of 25 symbols can the transmitter generate if symbols can be repeated in the message? So this is going back to earlier parts of this presentation before the binomial theorem. And this is, combinations with repetition. How many if 10 of the 40 symbols can appear as the first and or last symbols of the message? Other than 30 symbols can appear anywhere. Okay, so with repetition allowed, there are 40 to the 25th distinct messages. So that's the permutations with repetition. However, by rule of product, if you start looking at the second part, how many if 10 of the 40 symbols can appear only as the first and last symbols? So you can see that there's 40 for the first, and then 30 for all of the ones in between, because 10 of the 40 symbols can appear only as the first. So there's 10 of those. So you have 40 squared times, by the product rule, 30 to the 23rd. So you can see this second half right here, product ruled with the first half of this problem. That's just a standard combinations, permutations with repetition problem. Permutations with repetition. We've already seen this one, the Braille problem. We've already looked at that, so I don't know why we're looking at that now. These are good problems. These are good problems. In fact, this has been on the final exam many times. So what do we have to do here? You can see that this, what is your clue here? The clue is this looks like the binomial coefficient, the formula for n choose r. So in order to get that n choose r, we need somehow an n factorial on the top. So you can see how we do that. So we start with this thing, and then we needed an n factorial on the top. So we multiply the thing by 1, which is n factorial over n factorial. Because the sum of the factorials is the sum of the factorials, we can put that numerator in there and keep this denominator out here. But here, by doing this, we have formed the binomial coefficients. And the sum of the binomial coefficients times this factor that's left over is 2 to the n over n factorial. That's a good problem. This one, I think it's obvious if you look at it that there's alternating -1. And so that evens out by symmetry of the binomial coefficients to 0. They're alternating plus, minus, plus, minus, plus, minus, depending on what the power is at the particular time in the summation. Okay, those are good problems. You look at those and look at more. Hopefully you're doing all the at least odd exercises. That would be nice if you did that. Okay, all right, I don't know, where is it? Where am I? I am here, I believe. Yeah, that's where I am. I hope you see me. Anyway, that's the end of this reading break, as it were. We'll continue on with the remainder of Chapter 6 next week. And until then, enjoy what's left of your break and enjoy yourself. Goodbye.